So have you ever just looked up at a jet roaring overhead, or maybe seen a massive power plant on the horizon, and wondered, what's the secret? What do they all have in common? How do they turn simple fuel into just incredible power?
I mean, it seems impossibly complicated, right? We're talking about some of the most powerful machines that humanity has ever built. But what if I told you that at their very core, they all follow the exact same, surprisingly simple principle? Yep, you heard me. A recipe, it's a thermodynamic process that, once you get it, it unlocks the secret behind pretty much how our entire modern world is powered. It's the engine of, well, almost everything.
So here's what we're going to do. We're going to break down this universal recipe. First, we'll get right to the heart of power itself. Then, we'll see how that recipe literally takes flight in a gas turbine and how a different version of it powers our cities with steam. And finally, we'll look at the clever engineering tweaks that make it all even more efficient.
Okay, let's get right into it. We're starting with that universal recipe, the foundational principle that makes everything else we're going to talk about actually possible.
And here it is. Just remember, squeeze, heat, spin. First, you squeeze a fluid. Could be air, could be water. Packing its molecules together, building up all this potential energy. You know how a bicycle pump gets warm when you use it? That's what's happening. Second, you add heat. A ton of it, usually by burning fuel. This makes that compressed fluid super energetic and honestly just desperate to expand. And finally, you let it spin. You channel that high-energy fluid through a turbine. Think of it like a really, really advanced pinwheel, forcing it to rotate and generate useful work. Squeeze, heat, spin. That's it. That's the core recipe.
Now let's see this recipe out in the wild. First stop, powering flight. To get a massive airplane off the ground, you've got to understand the gas turbine. Now, engineers have a formal name for this process. They call it the Joule Cycle. And it's basically the official blueprint for turning heat into work using a gas. Its core steps? You guessed it. Compression, heating, and expansion. It's a perfect match for our squeeze, heat, spin recipe.
Okay, so let's look inside a jet engine. Right at the front, you've got these massive fans acting as the compressor. That's our squeeze. Then fuel gets injected and boom, ignite it. That's the heat. The hot gas that results expands like crazy, and first it spins a turbine that's actually connected back to the compressor, which is what keeps the whole thing going. Then all the rest of that high-energy gas blasts out the back. That's the second spin, and it's what creates the thrust that pushes the plane forward. It's just a beautiful self-sustaining loop. But, you know, there is always a gap between a perfect engine on paper and a real one bolted to an airplane wing. So how do engineers measure that gap? Well, they use a concept called isentropic efficiency. You can think of it like a report card, really, a score from 0 to 100% for how well a real machine works compared to some ideal, totally frictionless version. See, in a perfect world, 100% of the energy you put in does useful work. But in the real world, you've got friction, you've got turbulence, you've got heat loss. It's like a tax on your energy. So every real-world compressor and turbine has an efficiency score that's always less than 100%. And that means we get less power than the ideal math says we should. This is the constant battle that engineers are fighting.
All right, so we've seen how the recipe works for air. But what about the power plants that light up our cities? Well, they use the exact same core idea, but with a totally different main ingredient, water. And this is where we get into steam cycles. Now, these machines look completely different, but the principle is identical. Instead of air, a steam cycle uses water. Instead of burning fuel inside the fluid, it uses a big external boiler to heat the water into high-pressure steam. And this is a key difference, the water actually changes from a liquid to a gas and then back again. But don't let the details fool you, it's still squeeze, heat, spin at its heart. Now, you might be thinking, isn't there a perfect cycle that's the most efficient possible? And yeah, there is. It's called the Carnot cycle. But in the real world of steam power, it's a total disaster. Trying to compress this bubbly, wet mix of steam and water is incredibly hard. It takes a ton of energy, and it would just destroy the machinery. It's just not practical at all. So engineers had to come up with a much more clever solution. And that solution is called the Rankine cycle. It's brilliant. Instead of even trying to compress that messy, wet steam, the cycle just lets it fully condense all the way back into liquid water. And here's the trick. Compressing a liquid with a simple pump takes way, way less energy than compressing a gas. This one clever change is what makes large-scale steam power possible. Okay, so we've got our two main recipes, one for flight and one for the grid. But you know engineers, they are never satisfied. So how can we tweak the recipe to get more power out for the same amount of fuel?
This is where the really clever modifications come in. Like, instead of one giant squeeze, what if you use two smaller compressors and cool the air down in between them? That's called intercooling, and it makes that second compression step much, much easier. Or on the other side, what if you heat the gas a second time halfway through the turbines? That's called reheating, and it gives you this extra boost of power. These are the kinds of hacks that squeeze every last drop of efficiency out of the basic recipe.
And we're not talking about tiny improvements either. The source material for this actually calculates that just by using a two-stage compressor with an intercooler, you can save 12.6% of the energy needed to do the work. That is a massive saving in fuel and a huge boost in efficiency, all from adding just one clever step to the recipe.
And this quote here from one of the sources, it really captures the engineering reality perfectly. Our simple recipe analogy isn't just a metaphor. It's literally how these systems are designed. It's a series of distinct steps: compression, heating, expansion, each happening in its own specialized part, all linked together to create one powerful cycle.
So this principle, squeeze, heat, and spin, it's been the thermodynamic bedrock of the last century. It's what took us to the skies. It's what electrified our civilization. But as we look to the future, it leaves us with a really critical question. What new cycles, what new recipes are we going to need to power the next one?